Today we are going to talk about transmission electron microscope image enhancement using free electron-photon ponderomotive interaction. This name is not very catchy. Simply speaking, we are going to see how shooting laser on electrons make images good. Let's start by seeing how does a transmission microscope work. This explanation applies both for regular optical microscopes and for electron microscopes. An incoming plane wave is approaching the sample we want to image from the left. The sample scatters or absorbs parts of the wave, and so the intensity of the wave after the sample changes accordingly. If we measured the intensity of the field right after the sample, the intensity as a function of position would be our image. However, the sample is small, and so we cannot probe the field at such small scales. Therefore, we use optics elements to take the field and magnify it as it is. The magnified field hits the camera, which measures its intensity. Since the optics copy the field exactly as it is, the intensity pattern on the camera equals exactly to the pattern right after the sample. It is not always that easy. Sometimes, objects we want to image do not scatter or absorb the incoming wave, but only delay it a bit. You can think of imaging those objects like taking a picture of a clear glass on a white background. The light travels slower in the glass, but the glass is transparent and hard to see. Such objects are called phase objects and are common in electron microscopy. Since the wave slows down in the object, it acquires more phase when passing through it and the wavefronts are distorted. Let's observe the effect of the phase object on the wave in the complex plane of amplitude. If we could scan the field right after the object, we would see the phase delay induced by the sample as a rotation in the complex plane. Since the absolute value of the amplitude does not change when being rotated, the intensity is constant across the wave. And what would be the resulting image? Since the camera is sensitive only to intensity, the resulting image will be a constant white. We lost all contrast. In order to solve this problem, let's change our mathematical description of the outgoing wave. Instead of thinking of it as a complex number that slightly rotates in the complex plane, we can represent the same behavior as a constant unperturbed number to which we added a small almost perpendicular perturbation. Just as we decomposed the amplitude to a constant unperturbed complex number and a perturbation, we can decompose the whole outgoing wave into the unperturbed wave plane, which is drawn here in orange, and other perturbation plane waves that are drawn in blue. Note how in between the lenses, the different components of the wave are spatially separated. We can take advantage of this spatial separation to manipulate only the orange unperturbed wave. It is now time to introduce our solution to the problem, the laser phase plate. By placing an intense laser right at the focal point of the lens, we can shine laser almost purely on the orange unperturbed wave. Electron component that goes through a laser experience an effective higher potential energy, and therefore travels slower than components of the electron wave that pass by the laser. This adds relative phase shift to the unperturbed wave. The phase-shifted unperturbed wave is drawn in purple. Let's see how introducing the laser solves the problem. Recall how the amplitude behaved on the camera before introducing the laser. It was just rotating in complex plane, right? Well, now, since the laser induced a phase shift to the unperturbed component alone rotates in the complex plane. Specifically, we choose the intensity of the laser such that the rotation is exactly half pi. Now the unperturbed and perturbed components are parallel to first order. Now, when scanning the field across the camera's plane, we see that the two components interfere constructively, and so the absolute value of the amplitude is no longer constant. When the camera will measure the intensity, it will measure a photo which is no longer constant, and so we are finally able to see the phase object. But can we do better? Due to camera's technology limitation, we can further improve the quality of the image by not only delaying the unperturbed component of the wave, but also to attenuate it and to darken the background of the sample. Luckily for us, there is an energy filter in the microscope that knows how to throw away electrons with different energies than the original electron energy. If we could only give or take some of the energy of the unperturbed wave, it would be filtered out later by the energy filter. The current setup does not add or take energy from the electron, but only delays it. Let's see what happens when we rotate the laser slightly and put two different wavelengths of light. The red lines of the laser represent nodes of high intensity. Since there are now two different wavelengths, the intensity beats, and the intensity nodes propagate in space. Looking closely at the intersection point, we see that one can choose the angle of the laser tilt such that the electron's wavefront surf on the intensity nodes. Each electron's wavefront experiences a constant intensity, which is different intensity than that of the following wavefront. Let's see how the beating affect the phase shift to the unperturbed wave. Earlier, we had a single frequency laser, which caused a constant phase shift to the unperturbed wave. Now, when the laser beats and each electron's wavefront experiences a different intensity, the phase shift itself is oscillating with time. We are left to show how this time-dependent phase retardation, together with the energy filter, will attenuate the intensity of the image. Since now the electron's wave has a phase delay which oscillates in time, we can use Fourier transform to decompose it into a sum of different components, each one with a trivial well-defined frequency. Let's see this effect on the energy spectrum of the electron, together with its total complex amplitude. Before encountering the laser, all of the electron's wave function was concentrated in a single energy. Now, as we turn up the laser, it decomposes into a sum of many energies. As the energy filter will filter out all the energies which are not the original one, we will be left with attenuated amplitude of the original unperturbed wave. Now, when the camera will measure the field's intensity, there will be no bright background to the object, and the image will contain only the signal itself. Thank you for watching. To hear more about our work, search Osip Schwartz Lab in Google.